Okay, so welcome everyone again to your own channel, that is the AP Physics. So let me 1 second, please. Okay, so welcome everyone again to your own channel, that is the AP Physics. Please, anyone in the Zoom, comment me, or on the YouTube if you're present, please, you have a live chat present there. Please comment there if it's not audible. So, welcome everyone again. Please, you have a live chat present there. Please comment there if it's not audible. Yeah, it's truly audible now. It's great. Thanks. So now we'll see. We have completed our previous question. So in the series, now we'll find a very interesting thing. That is the force on a mass. Okay, just a while, please. Yeah. So, okay. So now we'll see force on a mass that is symmetrical system. Okay, let's start it, please. So you can also take the notes in the live session. This is like a live classroom. No worries in that. There is no skipping in this, no skip of the things. Okay. Now students will see forces on symmetrical structures. Okay. Let's start with the very basic and very interesting. Suppose we have a four masses. Suppose we're having a four masses on the vertices of square. Okay. And square edges or the square side length is capital L. Okay. So now, if the question arises that on the center of the square, a capital mass M is placed. That is, on the center of the square, a capital mass M is placed. And if you have been asked to find the net force on this mass, so let's solve it. We can see that the line joining this and this mass, and the line joining this and this mass, line joining this and this mass, line joining this and this mass, let's say A, B, C, D are all vertices. Okay. So at the center, if you check, attractive force will be this, attractive force will be this, and this. Now, if you find the net sum, you'll get, we can just by visualizing this expression, that is F, 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 F. So these two will be having their net like this, and these two will be having their net like this. This basically cancels. We'll say F net is equals to 0. F net is equals to what? It's 0 here. You can take any other cases too. So we can say like this, suppose I'm taking a triangle now, equilateral triangle basically, because square is a symmetric structure, equilateral triangle is also a symmetric structure. Okay. I hope I'm audible in the Zoom session or in the YouTube. Please comment anybody in the chat, live chat, if there is any noise issues. Okay. So now we'll see equilateral triangle case. We know that for equilateral triangle, angles are equal. All angles are what? These are equal. Okay. Okay, students. So if at the center the mass is this centroid, you can say centroid. Geometrical center is what here? Centroid. So just by we know the property of symmetric forces. I mean the force on the symmetrical structures, that is net force will be zero. You can also find it out here. This attractive force will be this, line journey is this force. I'm doing it fast, this force. So the net of these two forces will be anti-parallel to this vector and same in magnitude. So we'll say if this is something as F naught, the net sum of these two forces, that is for the attractive forces by vertices M mass B and M mass C, will be also what? F naught. So net will be what? Zero. So directly for the symmetrical structure, for the symmetrical system, you can write the F net force is equals to what? Zero. Okay. Please note it down. Now there is a question for you. So now please find it out. So what do you think? What will be the force on a mass at the center of hollow sphere? I mean, you're having a big hollow sphere, but having the mass density inside, all the mass density is at the periphery portion. So at the center, if I am keeping a small mass m, test mass small m naught, unit mass, you can say, what will be the net force? Yes, any answers, please? Anybody in the live chat or in the Zoom chat? Good. So we'll say here that for the hollow sphere, if we check it out, suppose this is a hollow sphere. Now all the mass is present at the periphery on the upper layer. Inside mass densities, there is no mass density, no mass is present. It's a hollow sphere. At the center, M naught test mass is present. So by the symmetrical property for gravitational forces, you can see, and let me take a small dm mass here. So this will attract it. So just anti-parallel to it. I mean, you can say like this, just opposite to it in front, there will be also one more dm, the same dm mass. Dm is basically same only because it's infinitesimally small mass. So this will also attract it. I mean, this will also attract this M naught. So net is what? Net is zero for these two dm, small dm masses. The same holds for all other dm masses. We know if we take this dm and integrate throughout the body, you will get what? The capital mass M of what? Hollow sphere. So we'll say net force is equals to, on this m naught mass is equals to, again, zero. Okay, please note it down. Okay, my dear students, now we'll understand a very interesting topic, that is okay, gravitational field. What is this gravitational field? So suppose you are having a capital mass m like this. This is your capital mass m. So suppose I'm bringing m naught test mass from say infinity near to it, say at r distance from center to center. Okay. Although we are neglecting the dimensions of the masses, we are assuming in this chapter that the dimension of this masses in the gravitational chapter is basically negligible. Length, breadth, height, or area, surface area. No, we are not. We're treating it to be point masses. Okay, same is treated in electrostatics too for the charges. We'll see in the future. So we'll say the amount of force which is felt or experienced the amount of force or the force which is felt or experienced by this m naught test mass when this m naught is in the vicinity of this capital M defines the gravitational field or the gravitational field strength of this capital M mass. If it's weak, we'll say at this r distance, the force field strength is weak. If at this r distance, the unit of force is what? It's Newton. So we'll get a conclusion. We'll get to the conclusion that gravitational field at r distance is powerful. It's strengthful. Okay. So now we're able to conclude the physical significance of gravitational field of a capital mass M. But how to mathematically do the interpretation of this mass, that is the gravitational field of this mass? For this, we'll understand gravitational field intensity. Okay, please note it down. So no worries, I'll be not erasing the things. Just write it here, gravitational field intensity. So I'll write it and end the session. Gravitational field intensity, E, sometimes in the book, it's given as capital I, is defined as the same, this force experienced by this m naught mass. Okay. So we define it as mole. See, very interesting point. This gravitational field intensity is actually for this capital M mass. Whose intensity is this? Whose gravitational field strength is this? Of this capital M mass. But in this expression, mathematically, the mass which is coming in the denominator is basically this M naught mass. Remember this point. Okay. So if we talk about the SI unit, its force is Newton, mass is kg. We will say Newton per kg is the SI unit of this gravitational field intensity. Okay, please note it down. Okay, so now we'll be solving for a generalized case, that is a capital mass M. Okay. So now let's see for capital mass M. Okay. Suppose we are having a capital mass M and at r distance, m naught test mass is present. Okay. So you have to find the expression for gravitational field strength. Let's find it out. We know this is a capital mass and this is a small mass m naught. So gravitational force magnitude will be G m upon r square. Now if we divide this with this one, test mass m naught, we'll get G m r square. Dear friends, this is a right out. So we have force by m naught as gravitational field strength intensity. Gravitational field intensity. So please remember this expression. So gravitational field intensity for this capital M mass is given by this expression. Please note it down. Okay, dear students, we'll meet in the next class. Thank you so much.